Connected Components Workbench, Micro800 Controller Programming. Now we're going to discuss a little lab project on approximate page 145 or so in the manual. Keep in mind that these page numbers change as we make changes to the manual. There are always more timers. And this little lab project specifically exercises TON and TOF instructions against the TON and TOF data types. In the manual, this was entitled More Timers. Although there are 8 timer instructions available for the Micro800, we're not going to do lab projects with all 8. What we did do in this lab project, More Timers, is we began with the previous lab project, which was the garage door opener control system. And I had you create this single rung of logic. In other words, delete all the rungs of logic from sequence. We're going to keep our buffered inputs and buffered outputs, and then put in just this one rung. Now the tag names are still what they were for the garage door opener, stop push button and motor up. The reason that we have a true if on and an energize output is that we want to see some action when we flip the switch connected to input 0. We want to see the indicator that's connected to output 0 light up whenever the timer is done. In other words, when Q, output from TO1_1 goes true. Now notice that we use the default name for this instance of a TON data type. If you add a timer to your logic, it comes up TON_1. If there's another one, then it's _2 and so forth. We really don't care about the name. But I did have you go in and edit the tag names. And to do that, I had you open first look in the local variables to see what's in the local variables. So double click on local variables. And you see the only thing that we have in local variables pertaining to this lab project is the timer, and that's fine. We don't need that in global variables. Now we'll select global variables, scroll down, and you see the alias tags that we were working with. The first one I had you change, which was stop push button, I changed it to start timer. So I click here and type in start. You can put a space in there, or I'm sorry, not a space, but an underscore if you like. And we called this start timer 00. It could have been 01 because we're starting timer 1. But this is what I did in the manual, so I'll just leave it that way. Then we went down to output 0, which is motor up, and put the cursor there. We can delete first if we like. And then we named it timer done 00. Hit enter. Now we'll close, or rather go back to our sequence, and you can see that they aren't changed here. This is a weakness that I hope they fix in Connected Components Workbench. I'm going to try different ways of trying to refresh this to see if I can refresh it without actually going and reselecting input 0. So I'm going to save. I'm going to close this. I might as well close the variables too. We don't need those. Now we're down to our 850 page, our start page. So now I'm going to double click on sequence. And you see now it comes up with the correct aliases, simply because when you open up this program file, in order to build the graphics on the screen, it went to IN00 and OUT00 and brought with it what it found in the data table that we had already edited. So the refresh in this software, once you make changes or edit tags, isn't quite up to where it could be yet, but it will be, I'm sure. I had you save, download, and go online. Downloaded, connected in the run mode. It was probably unnecessary to show you this, but it was in the manual, so we included it. If I push input 0, now I want you to notice that the ET starts accumulating. If I let off of the push button, because remember, my digital field device simulators, each input has 4 states: maintained on, maintained off, momentary open, momentary close. I'm going to push the push button, and let go. You see it doesn't quite make it to 2000 milliseconds. The output never comes on. If I flip it on and leave it on long enough to reach an accumulated value of 2 seconds, 2000 milliseconds, then the output goes on. Back offline to make the next edits. With RS Logix 5, 5500, we'll just say with RS Logix, you had a timer timing bit available to you from the timer data type. You do not with Connected Components Workbench. They may add it at some point, but currently it's not there. If you need a pulse, then you can use a pulse type timer instruction that puts out a pulse for whatever PT is, the preset value. The input goes on and you get that pulse length out. However, if you need to use a bit that's only on while the timer is timing, but not of a specific length, but it could be a specific length based on the PT, then we're going to add some logic to give you that. Now keep in mind, TON has to stay enabled. This input has to stay high. In other words, a true rung in order to keep it accumulating and for this logic to work. So I'm going to add a branch around. I must have dropped it in the wrong place. And I'm going to put in a true if off and a coil. One thing about Connected Components Workbench, just clicking to drop it in there may not work depending on where the focus is at, because I need to pull this inside of the branch. With the focus here, we click on an OTE and we've got another OTE. In this one, we're going to make this output 1. However, the name motor down doesn't work for us. We could right click, go to variable selector, go to motor down, delete that, and then type in TON01 timing. TON01 underscore timing. And this we want not Q. So we go to TON, we pick that, and then if we put a decimal point after it, we immediately get all the tags. So right there's TON underscore 1 dot Q. The logic reads then, if input 00, then enable this timer, and it starts accumulating. And if not TO underscore 1 dot Q, then TON01 underscore timing. Save this, download, and go online. Here's our project as was shown in the manual. There's actually one more thing that we could have added, and I think I'm going to, well, quick demonstrate this, and then I'll come back with one more thing added to make this identical to the timer data types in RS Logix. But for now, I'm going to push the button attached to input 0, and you'll notice that when the ET starts to accumulate, that the timer timing bit, output 1, will energize. See, it's energized. I let up before it times out. It goes off. So I'm going to hold it down for 2 seconds, and you'll see as soon as the done bit comes on, the timer timing bit goes off. That's exactly how the timer data type worked in RS Logix. I'm going to make one more change, which is unnecessary, but just for grins. I added a branch around with a single instruction in it that's named Timer 1 Enabled. With the RS Logix timer data types, you had an enabled bit, a timer timing bit, and a done bit. In looking at this, you would say, well, the Timer 1 Enabled bit is synonymous with input 0. Well, that is true. However, if you had more than one condition starting this timer, in other words, at the beginning of the rung, if you had more than just N00, then the enable bit here would not be a duplicate of one of those bits. It would be the collective state. If you need a bit that represents the timer being enabled, this is how you would do it. So here we have logic to give you a bit that comes on when the timer's done. Now that's really synonymous with Q. So you can actually just use .q, TON underscore 1 .q right here, this memory location, and use that wherever you would want for a done bit. Not a true if off, just use this memory location as the bit that goes on and off when the timer's timed out or not timed out. So here are the 3 bits that you would have with a RS Logix type timer. I'm going to leave this in here because it's not hurting anything. Notice that I did not use up one of my precious few indicators, output indicators attached to outputs for this. I just used a bit in memory. And you'll notice when I turn input 0 on, enable goes on right away along with timer timing. Now the reason you see a little delay between enabled and timer timing is that is just the way the Logix read, and then the screen is updated. See, there they went on together. So it has everything to do with the synchronization of the video card in your computer and your screen. But when input 0 goes on, that first instruction is true, it starts the timer, it starts accumulating, the enabled bit goes high, and the timer timing bit goes high. Once it's timed out, the timer timing bit's going to go off, but the enabled stays on because the timer is still enabled. There you have the basic function that we showed in the manual. Now I'm going to go offline and make some more edits. We added another rung of logic. I know it's some screwy looking logic. You have if timer, start timer, or rather if input 0 and Q, then done. If not, then timing. Before we execute this logic for the TOF, and of course we only have one input that we're using, so it's going to operate both the TON and the TOF. But before we do this, remember that I said when a TOF is done, it's not really done. It hasn't even started yet. But then once it is done, finish counting, then it's not done anymore. I suppose that using the .q instead of done may work out better logically in explaining this to people than what we do with RS Logix. So I'm going to turn on input 0, and you'll see in the upper case the TON times out, the enable bit stays on, the timer timing bit went off, and the done bit is on. Let me reset that. Watch the bottom rung. Rung goes false and it times out. This is the at rest state. So I'm going to turn it on again, and notice that nothing happens in the bottom rung other than the done bit comes on immediately. As soon as you turn on input 0, output 2 comes on immediately. So .q goes true the instant that N goes true. But nothing happens. It's done, but it's not really done. So now let's turn off input 0 and watch the timer timing bit and the done bit are both on simultaneously, and then they both go off. This is a method of creating a timer timing bit. Now the only reason this logic works is because, I'll do this again, when I put on input 0, notice that the output Q goes true immediately. However, input 0 is going to go off, which that instruction will now go false. The instant that I turn input 0 on, Q became true, turn on the done bit, but because input 0 is on, the true if off in the branch around for true if off, input 0, output 3, that rung is now false. When I flip it back, in other words, I turn off input 0, Q is still high. And that's what allows that logic to work, to give us a timer timing bit as long as Q remains high. Both cases, if Q is on up here, in other words, if it's done, then it's not timing. Down here, if it's done and it's accumulating, then it's timing. And then when it's not done, it's not timing either. So there is a little bit difference here in how the done bits function. But both of our timer timing bits do give you an output when the ET is accumulating. The goal here using timer data types, timer instructions, is really simple. We want to create something that either delays something going on. In other words, we don't want something to go on until after a length of time has expired after an event. So you have event, then you have a timed interval, then you have another event. That other event could be anything, but a TON is an on-delay timer. An off-delay timer, you have an event, but nothing happens. But when that event goes away, in other words, when that first event goes off, then there's a time delay before the other event goes off. So on-delay, off-delay. The enabled bits that we created, which are available with RS Logic's timer data types, that's just inherent, intrinsic in the data type. We showed you how to do those if you need an enabled bit. In other words, a bit that is on any time that TO1_1 is on. Now you could use the .in as well. If we go to local variables and expand this, you see we can use that bit right there as the enable bit. The only reason that I included this other business in the lab is for RS Logic's users if they're really stuck on the idea of an enabled bit. In both of these, we can create an enabled bit by simply branching around this instruction. Keeping in mind that the TOF is a little bit different because enabled means that it's queued up, but nothing's happening until it's not enabled. In other words, if it's disabled, then the timer starts. So A, we want to delay between two events, or we want, and that could be delay on or delay off. And the other is to create a pulse of a certain length that starts with a certain event, timer timing bit. And I've showed you how to do all these here. Now, we're going to change up the logic one more time to demonstrate how we can use a TON instruction to give us the TOF function. Here we are with our edits, and these edits can be found approximate page 149, 150, 151 in the manual. Remember that those page numbers can change. Our goal here was to show you how you could use a TON instruction, and by manipulating the logic of the bits, you could make the bits behave the same as identical bits for the TOF. The reason that we did that with RS Logics was because there was only one timer data type, and it supported or backed all timer instructions. And that data type had a done bit, and the done bit worked okay for on delay, saying that the interval was done. But in order for it to work correctly for a TOF, the done bit went on immediately and then went off after an elapsed time after the rung went false, delay off. That was a bit confusing. It was not unusual if you wanted an off delay to do something like rungs 1 and 2 here. Rung 3 is an actual off delay timer instruction with an off delay data type. Fortunately, instead of calling it done, they named it Q, which is just an output. That relieves the confusion somewhat. But for those of you that are dyed-in-the-wool RS Logic users and you relate to the done bit, then this is how you can use a on-delay timer to simulate the behavior of an off-delay timer. If we look here, we see that input 0 is off. Both done bits are off. Output 0 and output 2 are the done bits, so to speak, and then output 1 and output 3 are the timer timing bits. I'm going to flip on input 0, and you will see that what we're calling the done bit comes on right away. On both of these, the one using the TON, TO1_1 and TOF_1. The done bits from the TON and from the TOF behave identical. As soon as input 0 goes on, then those two done bits come on. Now I'm going to flip off input 0 and watch the timer timing pulse is true, and notice that the done bits go off together. Now you saw a little delay there on the screen. That's because I have a preset here of 2 seconds and a preset here of 4 seconds. I'm going to change that and then do this again. Here I am back. I had to go offline to change the preset on one of these to 4 seconds or 4,000 milliseconds, which is what was in the manual. Now let's do this again. I'm going to turn on input 0, and the only thing that happens is the two done bits come on, output 0 and output 2. And if you're using a digital field device simulator, you can see those LEDs illuminate. Those are your done bits. When I turn it off, what you should see is the timer timing bits energize and stay on until the ET equals the PT for both the TON and the TOF, and then they go off together with the done bit. So you see all four of them are on now, and then all four go off together. Top two rungs duplicate the behavior of output 2 and output 3, done bit and timer timing. Now there's no difference really between the Q of TOF and the done bit. You see, if Q is true out, then the done bit's on. However, up in the TON, we had to invert the state of Q for the timer timing bit. And for the done bit, we had to say that it wasn't done. So if you look at the very first rung, turn on input 0. If it's not done, then it's done. See, that's the behavior of an RS Logic's timer data type. For a TOF, when it's not done, it's done. Then when it is done, it's not done anymore. Very confusing. That's all I was trying to do here, and really, this was an exercise in logic for you to analyze. Knowing what we were after makes this make sense. If you didn't realize we were trying to make a TON behave like a TOF, this wouldn't make any sense.